Hello everyone, this is Sid from Sony. In this video, I'll be sharing in-depth details of a paper titled StyleAvatar, Real-Time Photorealistic Portrait Avatar from a Single Video, which was recently presented at SIGGRAPH 2023 conference. As the title suggests, the authors of this paper propose a real-time high-fidelity portrait avatar reconstruction method, which is also termed as the task of facial reenactment. So the theme of this paper revolves around performing the task of facial reenactment or portrait avatar reconstruction, which basically means generating photorealistic portrait images of a still source person given the expressions of a target person. Such algorithms target key regions to render, such as face, hair, neck, shoulder, and further fine-grained regions like lips, teeth, pupils, brows, etc. Before diving deep into the paper, I would like to summarize the key problems addressed by the authors. Authors provide hypotheses that existing StyleGAN-based portrait reconstruction methods fail to generate natural head movements in portrait videos as they mostly rely heavily on a highly aligned face dataset, which lacks sufficient variation in facial expressions. Also, such methods render the entire cropped face in one go, leading to a leakage of artifacts across different regions like background and foreground. Therefore, they reconstruct the full portrait video across three parts: facial region, non-facial foreground region, including shoulders, hair, etc., and the background region. Also, dealing with high resolutions of 1024 by 1024 involves a lot of computation and is generally very slow during inference. To tackle this issue, authors apply wavelet transform in all the subnetworks to replace high-res input image with a smaller 512 by 512 by 12 representation to achieve real-time execution with around 35 FPS on a desktop-grade gaming GPU. Finally, if the target person moves freely across the cropped frame, existing methods face the difficulty of texture tearing in the generated image. To tackle this issue, authors propose a sliding window augmentation technique to improvise the translation generalization, allowing the avatar to move freely in a larger range within the cropped image. They also crop the generated feature maps, ensuring the pixel-aligned relationship between the input feature maps and the output images. So briefly covering the related works, facial reenactment method falls across two categories. First is called single image based, which, as the name suggests, only takes a single source image as the input. In such methods, expressions are easy to capture, thus producing photorealistic results. However, shapes and details may not be consistent when animating to large poses and expressions, especially for those regions that have not been well covered in the single input image. Next is single video-based methods, which, as the name suggests, take the entire video as an input. They have shown to achieve more stable facial reenactment results. However, they are usually person-specific and have improved texture quality by utilizing 3D representations like meshes or point clouds. However, existing single video-based methods still face challenges in recovering elaborate details such as hairs, freckles, and even skin pores. So I would like to share one paper across each category. For single image based, a state-of-the-art paper titled PI Renderer maps the input motion descriptors to a latent space. It then generates a coarse image based on the motion estimated using warping network. Finally, the editing network is responsible for generating final image by editing the coarse result as an image-to-image translation task. Head-to-head plus plus is a single video-based method which performs 3D facial recovery of both source and target faces through 3D parameter estimation, specifically expression, camera, and identity parameters. These are then passed to an NMFC renderer, which produces the NMFC video. At the same time, the eye movements are mapped using landmarks of the source to detect and sketch the pupil region. Finally, a video rendering network is used to compute the generated video or the reenactment result. So moving on to the overall architecture proposed in StyleAvatar paper, the pipeline consists of three main stages. Stage 1, 3D tracking and rendering. So they perform 3D tracking to generate synthetic renderings with both predicted texture and UV coordinate vertex textures. Stage 2 is the feature generation stage, where they divide the portrait feature map into three parts: a static facial feature map, generated in UV space by a StyleGAN generator; a non-facial foreground feature map, generated from input texture rendering by a style unit; and a static background feature map generated by another StyleGAN generator. Then they employ neural textures to extract a facial feature map from the UV space and introduce a sliding window data augmentation to generate combined feature maps and better utilize the information from the entire video. Finally, another style unit is used to generate images from the combined feature maps, and a StyleGAN discriminator is introduced for adversarial learning. Note that only two style units are computed in the inference stage, and the reanimation is achieved by replacing the input expression and post parameters from another video. So let's discuss each of these stages in detail, starting with 3D tracking and rendering. They perform 3D tracking on the input monocular portrait video to generate pixel-aligned 3D renderings for subsequent training. For this task, they use an in-house 3D parameter estimation model called FaceVerse, which has also been published previously by the same authors. To supervise the training of mask prediction in the next stage, they generate foreground masks using an off-the-shelf architecture proposed in the paper titled Robust Video Matting. For 3D tracking algorithm, they solve for shape, expression, texture, translation, scale parameters, along with the rotation of the head and the two eyeballs. To improve efficiency, they directly solve the following objective functions of these parameters from landmarks of the target images. The three equations on the slide are solved using various matrix decomposition techniques. Here, KSRC are the landmarks generated by FaceVerse model, T-target are the target facial landmarks, and B-shape, B-expression, B-text are the respective bases. Further, two types of renderings are generated. First, a UV rendering with UV coordinate vertex colors for neural textures of the facial region. And second, texture rendering with predicted texture for non-facial foreground feature generation. To generate UV rendering, they use UV coordinate vertex colors, where red and green channel pixel values correspond to X and Y position in the UV coordinate space. To generate texture rendering, they utilize the predicted texture coefficients and render it with predefined fixed lighting in order to accentuate facial expression changes. In the feature generation stage, or the next stage, they divide the portrait region into three parts as discussed before. They use two StyleGAN-based generators to generate static feature maps for the facial region and background. For non-facial foreground region, they propose a style unit to generate pixel-aligned feature map from the input 3D rendering. Details on that are shared in the later slides. The facial feature map are generated in UV space, and input latent code ZID is designed for pre-training, therefore generating different feature map for different videos. They also incorporate a temporal latent code ZTemp as an additional input to style unit. The facial feature map is generated by sampling from the UV feature map using UV rendering. For the background and the non-facial foreground regions, they crop the generated feature maps using sliding windows to ensure the pixel-aligned relationship between the input feature maps and the output maps. To generate dynamic facial changes and protruding shapes like glasses, they directly add the facial feature map and the non-facial foreground feature map. To ensure that the foreground feature map is in front of the background map, they first use a supervised convolution layer to predict a foreground mask, and then combine these two feature maps using predicted mask. Finally, the combined feature map is fed to another style unit generator to generate the final image. The style unit proposed in the paper uses an encoder-decoder structure designed for image-to-image translation, with additional input latent code and noise. Similar to UNIT, the encoder extracts the multi-scale features that are sent to the decoder via skip connections. They use a mapping network, the modulated convolution, and the temporal latent code to introduce additional variation possibilities for the network, preventing it from smoothing certain features. The unlabeled modules, shown as orange and blue rectangles, represent two convolution layers with output channel and resolution labeled accordingly. The output is basically a three-channel photorealistic portrait image with a resolution of 1024 by 1024. As mentioned previously, they employ wavelet transform in all the networks to meet real-time requirements and speed up the training, similar to a paper called SWA-GAN. This technique replaces the high resolution output and the input image by a lower resolution representation. The blocks DWT and IWT are used for this efficient representation. Let's see how they use wavelet domain transformations. So, wavelet transform basically decomposes an image into a sequence of channels, each of which represent a different range of frequency content. The original model works with the first level wavelet decomposition, where each image is broken into four subbands: LL, LH, HL, and HH. These bands are attained by passing the image through a series of low-pass and high-pass wavelet filters and serve as the wavelet coefficients. The first subband, LL, corresponds to low-frequency information, and indeed, it is visually similar to a blurred version of the input image. The remaining subbands LH, HL, and HH correspond to high-frequency content in the horizontal, vertical, and diagonal directions, respectively. So by working directly in the wavelet domain, rather than image or feature space, the spectral bias of neural networks can be alleviated. As showcased on the image on the right, this technique also achieves improved visual quality and generates more realistic content in the high frequency range. SWA-GAN produces patterns that elude the state-of-the-art models such as StyleGAN2 even in an overfitting setup, where training set includes only a single image in this case of the slide. Another benefit of this approach is a significant reduction in training, iteration, and inference times, since an entire image is represented by a set of coefficients with reduced dimensionality. StyleAvatar uses the design based on SWA-GAN, where generator architecture predicts wavelet coefficients at increasing resolution scales, rather than predicting pixel values. And then an inverse wavelet transform operation turns the coefficients back to an RGB image. So in terms of loss functions, as direct supervision is feasible for their task, they utilize common L1 and perceptual loss with a VGG19 during the training process. Additionally, they incorporate an N1 loss for foreground mask. They also include a GAN loss for adversarial learning. The final loss is computed as the weighted sum of individual losses. The loss values are calculated by concatenating the pixel-aligned texture renderings with the generated images to create fake inputs for the discriminator, and they use the real image as the ground truth. So the model is pre-trained on a total of 6 videos cropped from a set of self-prepared 4K videos. And for a live system, a person's specific training methodology is followed, where they first pre-record an approximately 2-minute long video footage of a target showing several expressions. And the network is trained on this network video for the task of avatar reconstruction or self-reenactment, which is later transferred to the expressions of a driving video during inference stage. I have a video here which shows the training process in this view. So you can see first the subject records a 2-minute long video performing various expressions. Once the video is prepared, the data preprocessing stage starts, where the 3DMM tracking algorithm extracts the 3DMM parameters and the two types of texture and UV rendering are generated. So here the training process has started. You can see the style avatar is trying to reconstruct the ground truth with the minimum loss. So once the training has converged, they transfer it to an edge device for deployment. You can see the output for this particular case. The feed on the left is live, and the feed on the right is generated by the model. Okay, so the videos used in the paper include Obama video from White House public domain and a video sequence provided by a 3D avatar reconstruction paper titled I Am Avatar. They have also used videos from a dataset called MEAD or Multi-View Emotional Audio Visual Dataset. which is basically a talking face video corpus containing around 60 identities. The subjects talk with 8 different emotions at 3 intensity levels, and it contains around 7 view angles. There are a total of 281K clips of 1080p resolution each. Moving on to the evaluation part, to quantitatively evaluate their model, they have used three metrics. SSIM, or the Structural Similarity Index, which basically quantifies the perceived quality of generated image as a measure of similarity with the ground truth image. Second is PSNR, or Peak Signal to Noise Ratio, which is a very famous metric. It basically measures the quality of the generated output image. And the third is FID, or Frechet Inception Distance, which is a widely used metric for generative models. It measures the closeness of distribution between the real images and generated images using Inception V3 network layers. So they do two types of comparisons. First, they compare their method to state-of-the-art one-shot facial methods based on GAN structure to demonstrate the network's ability to achieve fine-grained control of expressions and facial details. They select two representative approaches, DAGAN as a 2D one-shot avatar generation method and Next 3D as a 3D one-shot method. DAGAN uses a set of depth-guided facial key points to map driving motion, whereas the Next 3D uses 3D parameters and a triplane representation to output 3D aware avatars using volume rendering. They capture two cases, self-driven animation or self-ID and reenactment or cross-ID. StyleAvatar outperforms DAGAN and both versions of Next3D in both image quality and control of facial attributes. These results suggest that video-based training is still necessary for high-fidelity portrait avatars, and their network structure shows better performance in video-based training. In terms of quantitative evaluation for self-driving animation, StyleAvatar achieves the highest SSM, IM, and PSNR, showcasing that generated fake images are closest to ground truth. At the same time, it achieves lowest FID, denoting better quality image generation compared to the other two methods. The second method of comparison is basically with four state-of-the-art video-based facial reenactment methods, including Deep Video Portrait or DVP, Nerve Face, Neural Head Avatar or NHA, and IM Avatar, all of which are trained on monocular videos. DVP uses a parametric representation of both input videos to drive expressions using monocular face reconstruction. Based on estimated 3D pose and expression parameters, Nerve Face uses volumetric rendering to synthesize the image of input face. NHA synthesizes the input 3D mesh using geometry and texture networks and optimizes the flame parameters to generate 3D reconstruction. Finally, IM-Avatar employs implicit morphing to find the nearest canonical surface intersection and predict RGB values by querying the canonical network. While the 3D methods show stable head geometry, they fail to produce high-fidelity texture details like hair, teeth, and pupils in the output renderings. StyleAvatar achieves higher image quality than the existing methods and can preserve more details such as light points in the eyes, as mentioned in the diagram here. As shown in the quantitative evaluation table, they achieve significantly better results, particularly in the FID metric, indicating that their method generates higher quality images. Also, the method is faster in training and rendering, while also generating images at a higher resolution. So I would like to show some video results as an output of their model. So the model is trained on the identity of the target actor, and in the output, the expressions of the source actor are transferred to the target actor. You may note here that for target actor 1, the region around the mouth is a bit blurry. So we'll discuss more about that in the limitations section. But in general, the model does a good job of capturing the expressions. while maintaining the identity of the target actor. So moving on to the section of ablation studies, authors also performed several ablation studies. I'll share two of them here. To investigate the performance with limited training data, they trained style unit with 50, 300, 1K, and 8K images, which were randomly sampled from the original training set. As depicted here, we can observe only a slight decrease in performance when the amount of data was reduced, specifically between 1000 images and 8000 images. Another ablation study to compare the training convergence time on different network configurations. They use the term DVP hours to refer to a simple unit with 3D texture renderings of their model, similar to DVP structure. For single style unit, they refer it to a style unit input with 3D texture renderings of their model. They also use a StyleAvatar model directly trained on target actor without any pre-training, as illustrated in the figure. Due to video decomposition and neural textures, they achieve significant faster training speed without any pre-training. The fourth column of ours without pre-train can learn the basic information of the background and the facial regions faster than the third column. Only the remaining regions such as shoulders, hair, and small parts such as eyeglasses and teeth require further training. Comparing hours without pre-train demonstrates the effectiveness of pre-training. So last section of failure cases, even though they achieve state-of-the-art results, but their model still has some limitations as described in their paper. First, their image-to-image translation is limited by the quality and variation of the training dataset. It cannot generate rotations and expressions that differ significantly from the training dataset, as shown in the first column of the figure. Second, the tracked 3D is not capable of accurately describing detailed expressions, leading to inaccurate expression control, as shown in the second column of the figure. Additionally, the mouth interior is not constrained, resulting in a lack of realism during the reenactment stage, with the inside of mouth sometimes appearing blurred, as we saw in the video output. Therefore, these could be a great avenues for possible research in this domain. So that is it for this video. The domain of facial reenactment also gave rise to a great question. What type of use cases facial reenactment can have across the industry or in our day-to-day lives, considering the ethical challenges involved with its deployment? Please feel free to type in your thoughts in the comment section. Thank you.